of mathematical stamps from around the world in my collection. And I usually start by mentioning a set of 10 stamps issued by Nicaragua in 1971 and entitled 10 Mathematical Formulas that Changed the Face of the Earth. As you can see, these range from 1 + 1 = 2 and the Pythagorean theorem via Archimedes' law of moments and Newton's inverse square law, ending up with Einstein's law equals mc squared. You'll see some of these again later on. So let's go back in time. My treatment is chronological, going back to the time when people first began to count and measure the objects around them. Early methods included forming stones into piles, cutting notches in sticks, and especially finger counting, which led eventually to our familiar decimal number system. Also, in several places, we find ancient geometrical arrangements of stones, such as the circular pattern of megaliths at Stonehenge and the linear arrangements at Karnak in Brittany. We don't know their exact purpose, but they may have celebrated astronomical events such as sunrise on Midsummer's Day. So we'll begin our journey with the mathematical achievements of Egypt, Mesopotamia, and Greece, all shown on this map. Here's Mesopotamia, there's Egypt, and Greece further on. In Egypt, the main achievements involve the practical skill of measurement. The magnificent pyramids, designed as tombs for their readers, attest to the Egyptians' extremely accurate measuring abilities. And the oldest of these, at the top, is King Joseph's Step Pyramid in Saqqara, built in horizontal layers and dating from about 2700 BC. Rather better known as the Great Pyramid of Cheops in Giza, constructed from over 2 million large blocks of stone. And amazingly, the sides of its square base, which are about 230 meters long, agree in length to within 1/100 of 1%. Our knowledge of Egyptian mathematics comes mainly from two fragile primary sources, the Moscow and Rhine papyruses, similar to the papyrus you can see here. The Moscow and Rhine papyrus include tables of fractions and problems in arithmetic and geometry, probably designed for the teaching of scribes. On the right, you can see the Egyptian god of reckoning, Thoth. Moving to Mesopotamia, early examples of mathematical writing also appeared there between the rivers Tigris and Euphrates in present-day Iraq. Top left, you can see an accounting tablet from about 3000 BC, where the thumbnail indentations at the top represent numbers. Later, the Mesopotamians wrote their mathematics with a wedge-shaped stylus on damp clay, which was then baked in the sun. Many thousands of these cuneiform tablets survive and show basic arithmetic and the calculation of areas and volumes in geometry, the solving of what we now call linear and quadratic equations, and an extremely accurate value for the square root of 2. Their number system was based on 60, which we still use for measuring time. And they also studied astronomy and observed comets, such as the one we now call Halley's Comet, although the date of 2349 BC is about 2,000 years out. Let's now move to more familiar territory. From about 600 BC, mathematics flourished in the Greek-speaking world of the Eastern Mediterranean. During this time, the Greeks developed deductive logical reasoning, which became the hallmark of their work, especially in geometry. Pythagoras, a semi-legendary figure, formed a school in Crotona to further the study of mathematics, philosophy, and natural science. His followers supposedly believed that all is number, quantifying many things, and emphasizing the four mathematical arts of arithmetic, geometry, astronomy, and music, which we'll meet again later. We don't know who first proved the Pythagorean theorem, that the area of a square on the hypotenuse is the sum of the areas of the squares on the other two sides, but its connection with right-angled triangles was already known to the Mesopotamians 1,000 years earlier. The blue stamp was issued very recently in August for the International Congress of Mathematicians in Korea. The scene then moved to Athens, which became the most important intellectual centre in Greece, numbering among its scholars Plato and Aristotle. In 387 BC, Plato founded a school in a suburb of Athens called Academy, and Plato's Academy soon became the focal point for mathematical study. It's said that over the entrance appeared the inscription, "Let no one ignorant of geometry enter here," like the Greek inscription at the entrance to this very building. In Raphael's fresco, The School of Athens, on the left, Plato and Aristotle appear together on the steps of the Academy. Plato believed that mathematics and philosophy were essential training for those holding positions of responsibility, discussing the mathematical arts of arithmetic, geometry, astronomy, and music, as I mentioned before, and justifying their importance. He also described the 5 regular or platonic solids, shown here in the middle. His pupil Aristotle helped to formalize the study of deductive reasoning, explaining why the square root of 2 cannot be written as a fraction, and also discussing logical syllogisms such as all men are mortal, Socrates is a man, therefore Socrates is mortal. Around 300 BC, following the military successes of Alexander the Great, mathematical activity moved to Alexandria in the Egyptian part of the Greek world. The first important mathematician there was Euclid, shown on the right, mainly remembered for his Elements. This most influential compilation of known results consisted of 13 books on plane and solid geometry, arithmetic, and number theory. A model of deductive reasoning, it started from initial axioms and postulates and used rules of deduction to derive new results in a logical and systematic order. And we mustn't forget Archimedes from Syracuse in Sicily. He was one of the greatest mathematicians of all time. Around 250 BC, he calculated volumes of solids such as spheres and cylinders. He listed the 13 Archimedean or semi-regular solids. These are polyhedra with regular faces, but of different types. And he also obtained a good approximation for pi by considering 96-sided polygons that approximate a circle. In mechanics, he found the law of moments for a balance that you can see on the right, and he's also credited with inventing the Archimedes screw for raising water from a river. In statics, he stated Archimedes' principle on the weight of an object immersed in water, as you can see in the middle, and he used it to test the purity of King Hero's gold crown. On discovering the principle, he supposedly jumped out of his bath and ran naked through the street, shouting, "Eureka, I have found it." But sadly, no stamp has ever been issued featuring that particular episode. We now move to China, where the mathematics dates back some 3,000 years. Around 220 BC, in particular, the Great Wall was a major triumph of engineering skill and mathematical calculation. Most ancient Chinese mathematics was written on bamboo strips, and you can see an example top left, showing a 9 by 9 multiplication table. For their calculations, the Chinese used a form of counting board, shown bottom left. A box with separate compartments for units, tens, hundreds, etc., into which small bamboo rods were placed in order to do the calculations. Chinese mathematicians were fascinated by pi. Around AD 100, Zhang Heng, who is the first of the three Chinese mathematicians you see up there, Zhang Heng invented a seismograph for measuring earthquakes. He gave the value square root of 10, which is about 3.16, which was a popular approximation in many areas. Later, Liu Hui, in AD 263, shown in the middle there, considered polygons with 192 sides to deduce that pi lies between 3.1410 and 3.1427. And here you can see in the middle Liu Hui's 9th chapter of the mathematical art, his edition of that. Then around the year 500, top right, Zhu Shongxi and his son considered polygons with about 25,000 sides to obtain pi to 6 decimal places. And they also found the value 355 over 113, also correct to 6 decimal places, and this approximation wasn't rediscovered in the West until the 16th century. But a similar situation occurred with Pascal's triangle of binomial coefficients, shown here, bottom right, which had appeared in a Chinese text of 1303, although in fact it was known earlier than that elsewhere. But even so, this was 400 years before Pascal. An ancient Chinese story of perhaps 1100 BC concerns Emperor Yu, who was standing on the banks of the river Luo when a turtle emerged with 1 to 9 on its back, with the numbers in each row, column and diagonal adding to the same sum, 15. This arrangement of numbers, the Luoshu, acquired great religious and mystic significance, and eventually led to larger such magic squares, as pictured on these Macau stamps issued only last month. Next year, 3 more stamps will be issued by Macau with the values 816, so that the stamp values themselves will form the Luoshu magic square, 492357, 816. They obviously have a mathematician in the Macau post office. Indian mathematics can be traced back to about 600 BC, when Vedic manuscripts presented early work on arithmetic, permutations and combinations, number theory, and extraction of square roots. And around 250 BC, King Ashoka, ruler of most of India, became the first Buddhist monarch. And in celebration, pillars were constructed. You can see one on the left, and then above you can see the capstone at the top of it, showing the earliest examples of what became our Hindu-Arabic numerals. A decimal place value system with the position of each digit 0 to 9 indicating its value, and enabling one to carry out calculations 1 column at a time, as we do now. The first outstanding Indian mathematician was Aryabhata, around the year 500, who showed how to sum arithmetic progressions, and also to sum the natural numbers and their squares and cubes. There's no stamp featuring Aryabhata, but there is one showing the first Indian space satellite, which was named Aryabhata in his honor. In later years, Indian mathematicians and astronomers constructed magnificent observatories, such as you can see on the right, such as the Jantar Mantar in Jaipur. Comprising 14 massive measuring instruments, it included the 90-foot Samrat Yantra, the world's largest sundial. We move now to the mathematics of the Arabs and Persians. United by their new religion, and with Baghdad lying on the east-west trade routes, Islamic scholars from 750 to 1200 developed Greek and Roman writings from the west, and Hindu writings from India. Some of our terminology dates from this period. The word algorithm, a step-by-step procedure for solving a problem, comes from Al-Khwarizmi, as shown on the left, a Persian mathematician who lived in Baghdad and wrote influential works on arithmetic and algebra. His arithmetic introduced the Indian decimal place value system to the Islamic world, while the title of his algebra book, Kitab al-Jabr wal-Muqabala, gives us the word algebra. Al-Jabr means adding a positive term to both sides of an equation to eliminate negative terms. Also influential among Islamic works were those of the geometer Ibn al-Haytham in the middle. Known in the West as Al-Hazm, he mainly worked in optics, and a celebrated problem is Al-Hazm's problem, where on a spherical mirror is light from a given point source reflected into the eye of a given observer. A century later, the mathematician and poet Omar Khayyam, on the right, wrote a celebrated algebra text with the first systematic classification of cubic equations and a discussion of their solution. They weren't solved in general until 16th century Italy. Omar Khayyam also publicly criticised an attempt by Al-Hazm to prove Euclid's so-called parallel postulate, which I'll be explaining later. In the West, he's mainly remembered for his collection of poems, the Rubaiyat. A later unsuccessful attempt to prove Euclid's parallel postulate was by the Persian mathematician Nasir al-Din al-Tusi, shown on this magnificent stamp there on the left, who wrote substantial works on astronomy and constructed the first modern observatory. He also wrote influential treatises on logic and theology, and his extensive investigations into plane and spherical trigonometry included the sine rule for triangles. During the 8th and 9th centuries, the Islamic world spread across the top of Africa and then up into Europe through Spain and Italy. Córdoba became the scientific capital of Europe, while Islamic decorative art and architecture spread through southern Spain and Portugal and included the magnificent geometrical arches in the Córdoba Mosque, which you can see on the left, and the tiling patterns in the Alhambra in Granada on the top right. Also in Córdoba, the geometer and astronomer Al-Zarqali, shown in the middle at the bottom, constructed many astrolabes. These consisted of a brass disc suspended by a ring that's fixed or held in the hand, with an attached rotating bar and a circular scale on the rim. And to measure the altitude of a planet or star, you view it along the bar and then read the result from the scale. But in Europe, the period from 500 to 1000 was known as the Dark Ages. The legacy of the ancient world was largely forgotten, and the level of culture was low. The revival of interest in mathematics began with Gerbert of Aurillac, who trained in Catalonia and introduced the Hindu-Arabic numerals to Christian Europe, using an abacus he designed for the purpose. A major figure in the church, he was crowned Pope in the year 999. That doesn't happen to many mathematicians. Top right, the Catalan mystic Ramon Lull believed that all knowledge can be obtained combinatorially by taking mathematical combinations of God's divine attributes, such as power, wisdom, goodness, etc. His combinatorial ideas later spread throughout Europe, influencing such mathematicians as Mersenne and Leibniz. A surprise appearance here is Geoffrey Chaucer, author of the Canterbury Tales, who also wrote on the astrolabe. This was one of the earliest scientific books in English. The Hindu-Arabic numbers were also popularized by Fibonacci or Leonardo of Pisa in his Liber Abaci, Book of Calculation. This famous work of 1202 contained many problems in arithmetic and algebra, including his rabbit's problem on the left that leads to the Fibonacci sequence, 1, 1, 2, 3, 5, 8, 13, and so on, in which each successive term is the sum of the previous two. These numbers also arise in the arrangements of seeds in sunflowers and pine cones. For example, there's a sunflower head there, and if you count down the spirals, you get numbers like 55 and 89 appearing. The ratios of successive terms of the Fibonacci sequence approach a limit, the golden ratio, which is about 1.618. It's the ratio of a diagonal and a side of a regular pentagon, and also a rectangle with sides in this ratio is sometimes considered to have the most pleasing shape, not too thin and not too fat. As shown on the Swiss stamp, top line in the middle, removing a square from a golden rectangle leaves another one. And this stamp also features the logarithmic spiral found on the north of the shell below. But also in a set from Macau is a stamp featuring a Penrose tiling, which I thought I would show you today, consisting of its two shapes, the kite and the dove. And if you want to see a Penrose tiling, you don't have to go very far.